The last topic that we're going to talk about here is what happens if you take a limit going to infinity. All of our previous examples, we were always approaching some number like 2 or 3 or 4. Now we're going to talk about what happens if we let x approach infinity or negative infinity. And I'm going to illustrate that using an example. A company training program has determined that on the average, a new employee produces P of S items per day after S days of on-the-job training, where P of S is a rational function, 75S divided by the quantity S plus 8. What I want to know is how effective is this training? So to start this problem, we really need to think about what we mean by effective. Let's take a bunch of values of S here and see what happens when I put them into this particular function. When I put 1 into 75S over S plus 8, I get 75 over 9, and that's about 8.3. After 1 day of on-the-job training, they produce approximately 8.3 items per day. After 5 days of on-the-job training, they produce approximately 28.8 items per day. If I put 28 into this function, so roughly a month, they produce approximately 58.3 items per day. What you'll notice is we're certainly doing better and better. More training means they produce more items per day. If I go to 260 days of on-the-job training, I get an increase from 58.3 to 72.8, but it's not that big of an increase. And if I go from 260 days of on-the-job training to 2,600, so that's 10 times as much on-the-job training. No one's ever going to have that much training. We only go from about 72.8 items per day to 74.8 items per day. It seems like things are kind of leveling off. As the amount of on-the-job training is increased, the daily production continues to increase, but at a slower and slower rate. This means that the training is becoming less effective over time. Because more effective would lead me to think that I'm getting those bigger and bigger gaps or increases in production, like I saw at the very beginning. If I make a graph of this, what you're going to notice is our production goes up very quickly, but then starts to level off. As I go farther and farther to the right, what exactly is it leveling off at? In fact, we're kind of looking for a horizontal asymptote here. What is that upper limit? What is the most that if we had infinite number of days of training, what's the highest limit that we could possibly get for production? So what we're asking for here is the limit as S approaches infinity. So as S gets very, very big, what's happening to that fraction? So when we say a limit at infinity, instead of getting closer and closer to some number like 6, now we're just making the numbers larger and larger and seeing what happens as we put them into the function. We can certainly make up a big table like this, and in fact we just saw that. It looks like we were getting numbers in the mid-70s, but to do this limit algebraically, we're going to divide each term in this fraction by the largest power of the variable in the denominator and do the limit of all the resulting pieces. The largest power of the variable in the denominator is 1, so I'm going to divide each one of these 3 pieces by s to the 1. I'm going to take the limit as s approaches infinity of 75s over s, s over s, and 8 over s. Since I'm dividing everything by exactly the same thing, I'm essentially dividing by 1. 75s over s is just 75. S over s is just 1. 8 over s does not reduce at all. And since this is a fraction and we have a sum in here, I can go ahead and take the limit of each one of these individual parts. So the limit as s approaches infinity of 75, the limit of 1, and the limit of 8 over s as s approaches infinity. Since 75 doesn't have any s's in it, it's just getting closer and closer to 75. It never changes as s gets bigger. So the top limit there is going to be 75. And the same for the limit of 1. It never changes as s gets larger and larger. So the value of that is going to be 1. But what about this next piece? Well, as s gets larger, or 8 over s is going to get smaller and smaller because it will like have 8 over 10, 8 over 100, 8 over a million. So this piece is going to get closer and closer to 0. What's left then is, remember, the top got closer and closer to 75. The bottom gets closer to 1 plus 0. So this whole thing gets closer and closer to 75. And remember, the table that we had seemed to be getting closer and closer to some value in the mid-70s. And now we know that what it is 75 right here. Even with an infinite amount of training, the highest daily production that we could expect is 75 items per day. What I'm really taking advantage of here is for any real positive number n, so this means things like 1, 2, 3, or 1.4 or 1.5, if I take the limit of 1 over x to that power as x approaches infinity, we're going to get 0. And the same if we approach negative infinity. So if I put bigger and bigger positive numbers or bigger and bigger negative numbers in here, this fraction is going to get closer and closer to 0. That allows us to do all of these limits at infinity that involve fractions. Here's our strategy. Suppose we have a rational function, p of x divided by q of x, and that the limits of f of x as x approaches infinity, the limit of f of x as x approaches negative infinity, we can follow the following steps to figure out what the limit of that fraction is. We're going to divide p of x and q of x by the highest power, or the x to the highest power, that we find in the denominator, q of x. Then we'll use these rules that we just talked about to figure out the things that are going to approach 0. Remember, the limit of constants are just going to be the constants. If I'm trying to find the limit as x approaches negative infinity of this rational function, first thing I'm going to do is I'm going to find the highest power that's in the denominator, and I see that it's 2. So that means that I have to take these 4 terms here and divide each one of them by x squared. We're going to take x over x squared, 2 over x squared, 2x squared over x squared, and add lastly 1 over x squared. When I reduce those, I get 1 over x plus 2 over x squared divided by 2 plus 1 over x squared. Now I can take the limits of each one of these, add them on top, add them on the bottom, and then divide the results. And I also have that constant on top that I can pull out in front. What that leaves me with is limits involving 1 over x and 1 over x squared. And remember, as x gets very, very negative, these denominators are going to be like 1 over negative a million. Those are all going to be 0. And that's what that last little rule gave us. I'm going to have 0 plus 2 times 0 divided by 2 plus 0, and that just gives us 0. So the idea here is when you divide by that power, we're going to get all of these 1 over things, and when I have 1 over a very large number, that's going to get closer and closer to 0.